Well, good morning, students. Let's finish our work on this chi-square test of association problem. Recall that we're looking at the Pfizer mRNA vaccine that was developed to reduce the incidence of COVID or prevent you from getting COVID. I mean, that was the idea behind the vaccine, was to prevent individuals from contracting COVID. And so in the study, you can see they had 18,198 individuals who were given the mRNA vaccine, and then they had 18,325 individuals who were given a saline placebo. Now, the study was reported in the New England Journal of Medicine. Let's take a quick look at that paper and see where I got these numbers. So I'll post this paper for you to download and save for your files if you're interested. Let's scroll down a little bit here, and we can see in the results we get some frequencies here, but we don't get the numbers we actually need. Although I do want to point out this. Notice that they're saying that the vaccine was 95% effective. Okay, so that sounds very impressive. Let's see where they got that statistic from in a little bit once we compute the effect size. So they're jumping right to the effect size here, and they're saying it's 95% effective, which sounds pretty darn good. Now let's scroll down and see where they got the data from, or at least where we got the data from in the paper. You need to find table 2 here. Here we go. So here are the, again, total individuals who took the vaccine and then the placebo. And here you can see 8 individuals contracted COVID with the vaccine, 162 people contracted COVID with the placebo. So this is where we got the numbers from the paper. So let's switch back over to the problem and finish working out our chi-square and find out where they got that 95% from. So notice here it is again. This is the vaccine efficacy, the 95%. And this is a little bit different from anything we've seen so far. This is a posterior probability. And notice here the hypothesis is the vaccine efficacy greater than 30%? And you actually want this type of probability to be high. So you want that to be close to 1. So that actually is good news for the vaccine, that it's highly probable that the vaccine efficacy is greater than 30% in the population. So this is a little bit different than anything we've seen before. But again, this is a posterior probability. Lots and lots of stats out there to learn. We're really just almost like scratching the surface in this class. But okay, let's return to the problem then. So recall our hypotheses here, the way we're going to write them for this chi-square test of association. We have the null hypothesis, the population correlation, or we could use the word association here, that would be fine too, is equal to 0. And then the alternative, the population correlation is greater than 0 or it's less than 0. And so we're going to write a little bit here indicating that we're predicting there's going to be a positive association. What we mean by that is that the mRNA injection will result in fewer positive COVID outcomes. Now, the opposite alternative would be a disaster for Pfizer. That would be if the mRNA injection resulted in more positive COVID outcomes. So if you took the injection, you were more likely to get COVID. Again, so that would be a disaster. So we're rooting here for a positive association. Now, we've already talked about this in class, but you can see that the data are in the predicted direction for Pfizer. So notice, if you were to take 8 and divide it by 18198, you're going to get a percentage, and that percentage is going to be smaller than if you take the 162 divided by the 18325. So in other words, proportionally fewer people are contracting COVID. Notice we're in the COVID row here, are contracting COVID if they took the mRNA injection rather than the placebo. So the data are in the right direction. So if this is significant, we're going to reject the null and conclude that there is a positive association. The mRNA injection is resulting in fewer positive COVID outcomes. If you've read the rest of the slide, you're going to see we're going to be concluding that. But let's work through the computations here. So in class, we computed these expected frequencies. So recall the formula there. I'll explain why that formula works in a later lecture. So again, the raw numbers here, the raw data, the frequencies, and then parentheses, we have the expected values. And along the edges here, we have the totals. So if you add up 8 and that number, you get that. 162 plus that, you get that. Add up these, you get 170 and so forth. And then they had 36,523 people altogether. So this is going to be significant unless it's exactly a chi-square of 0, which it isn't going to be. So we know that very well in this class. If you have a massive sample size, you're going to find significance. So the effect size then becomes even more important. Okay, so going to the chi-square observed, well, actually first, recall in class we got the degrees of freedom using this formula, so it's 1, and then we went to the table and got our chi-square critical value, 3.84. So we need to equal or exceed that to reject the null. So now we go and get chi-square observed. So here is the formula off your formula sheet. So let's walk through these computations here for a bit. So notice here the observed minus expected squared. So here's the first cell, 8 minus 84.70 squared. So there's the observed and expected divided by that expected value. And then now we go to the next cell, 162. There's the expected value. So 162 minus 85.3. Square that, divide by 85.3, and so forth. So here are the other two cells. Here are the intermediate computations. At the end, you get this whopping chi-square observed of 139.08. So as we anticipated, yeah, it's statistically significant. It's highly significant. If we were to get the p-value out of SPSS, it's going to be less than 0.0001, and it's going to be a tiny, tiny p-value. But again, we expected that, so we really need to get to that effect size here. We'll do that in just a second. But let's finish off the rubric like we've been doing in class. So I reject the null. It is statistically significant at the 0.05 level. And then it appears that in the population, individuals injected with the mRNA product are less likely to contract COVID compared to those injected with a placebo. And again, we reasoned through that a couple of minutes ago. Percentage-wise or proportion-wise, this is smaller. Taking the Pfizer vaccine, again, getting COVID, that's a smaller proportion than if you were to take the placebo. Now, this could be a type 1 or type 2 conclusion error because we've rejected the null and we do have a directional hypothesis here. So we'd have to replicate this study to make that determination. Okay, now let's move on to the effect size then. Now, I've got a lot on this page here, and I've actually got another one coming up because there are a number of effect sizes that we can compute for these 2x2 contingency tables. So here I've got the data shown again. Now the first effect size we'll look at, and this is on your formula sheet, is Kramer's V. Formula is pretty straightforward. Chi-square observed divided by n times k smallest minus 1. K smallest is the smaller of the number of rows or the number of columns. And here I've got 2 rows and 2 columns, so 2 or 2, it doesn't matter. So you can see the 2 then minus 1. And here's the chi-square, and then here is the total sample size, 36,523. Got it from right here. So plug and chug, and you get 0.06. Now this is a correlation coefficient in absolute terms. We'll get to that particular statistic later, but it ranges from -1 to +1. And if it's 0, that means no association. And recall our population correlation for the null hypothesis was 0. So this is pretty darn close to 0. So how is this vaccine 95% effective when the correlation is almost 0, indicating, again, no association? That's the null hypothesis. So even this tiny effect is statistically significant because we have a massive sample size, but it looks like a tiny effect. Well, welcome to the world of stats. This is a perfectly legitimate statistic, and this is a small effect. But it's not the only effect size you can report. And Pfizer did not report this effect size. They reported that 95%, which we'll get to in just a second. So this is the Kramer's V, and that's on your handout. So become familiar with this formula and how to use that. Okay, the next effect size I'll show you here is what's called the odds ratio, OR, odds ratio. Now it's a bit arbitrary how you set this up. So what I've done here is you can see I've taken 162 and 163 right here. So I've taken the placebo individuals, those who took the placebo and got COVID, those who took the placebo and did not get COVID. And then over that, I put that over rather, 8 divided by the 18190. So these two numbers in the denominator. So divide this, divide that, and then divide those two numbers, and you get 20.28. So work that out with your calculator and check it out. So go ahead and just say approximately 20. Now how do we interpret this? what you do is you look at the numerator here first, the top numerator here, and it reads those injected with a placebo, because that's what the numerator represents. I took it right here. So those injected with placebo, then I go here, are 20 times, just round it there, 20 times more likely to, now notice I'm here, getting COVID. Getting COVID compared to those injected with Pfizer's mRNA product. So we start here, those injected with placebo are 20 times more likely to contract COVID. Again, I could actually just use the 162 because that's the top number there. So that's the outcome of getting COVID compared to those injected with the Pfizer's mRNA product. So again, I said this is a bit arbitrary. I set this up. I could just flip that. So take these two numbers first and then put those over these two numbers. And I get 0.05. That's just a reciprocal of this. So if you take 1 divided by this, you're going to get this. And it's the same interpretation. So it doesn't really matter. Those injected, now notice how I reverse it though, those injected with the Pfizer's mRNA product are 20 times less likely to contract COVID compared to those injected with placebo. So again, this sounds pretty impressive now. I'm 20 times less likely to get COVID if I take the injection. That sounds like a big effect size. But yet, again, we've got this little tiny correlation up here. So which of these is right? Well, they're both correct. They're both perfectly legitimate statistics to compute from the same data. And these numbers, or if we focus on this one, this number seems like it's a really effective vaccine. But I look up here and it doesn't look very effective. But that's just the wacky world of statistics. Now we still don't see that 95% though. So where did they get that? Well, let's go to another slide. Again, we got the data here. Now let's do some quick basic math here. And this is what I mentioned before. So notice here, percent COVID if you took the placebo. So I take the 162 and divide it by the total number of people who took the placebo. So 162 divided by 18325 times 100, and that gives me 0.88%, 884%. So very tiny percentage of people who took the placebo actually got COVID. 162 divided by 18325 times 100. Now let's get the same percentage for those who took the Pfizer vaccine. Again, how many of those individuals got COVID? So it's 8 divided by 18198. So here you see that. And then multiply by 100 to make it into a percentage, and that's 0.044%. So these are pretty small percentages we're dealing with here, and you can obviously just see that by looking at the numbers. Okay, now that you have those two in hand, here's what you want to do. This is what's known as the relative risk reduction, RRR, relative risk reduction. And what you do is you take the risk of getting the disease using the placebo, if you just take the placebo, the saline injection. So we start out with a baseline of 0.884%, not very high, but then now we subtract the treatment percentage. So we take the 0.884%, subtract the 0.044%, and that is, you see, that's the change in percentage. So I start out with 88%, or 0.88% rather, if I don't do anything, just take a saline, and I can get that down to 0.044% if I use the Pfizer product. So there's the difference then in those percentages. And now you take that relative to where you started, the base rate. So that's why it's called a relative risk reduction. Here's the risk reduction relative to where I started. So you work this math out and you get 0.95. So there it is. There is the 0.95. Now that's a proportion here, and so we can go ahead and multiply by 100 and we get 95% efficacy. So there is the 95% reported by Pfizer. Okay, now that is a very popular statistic, but again, it's one of now 3, but we've got 2 more to go. So we had the Kramer's V, we had the odds ratio, now we've got the relative risk reduction, but there are 2 more. This is what's known as the absolute risk reduction, ARR. Very simple to compute. It's really just the numerator here. So I started at 0.884% if I just administered saline, didn't do anything, and then now I inject folks with the mRNA product. How much of a decrease is there? Well, 844 down to 044. that's a difference of 0.84%. So these are already percentages, so I'm not going to multiply by 100 here. So that is less than 1%. So that is the interpretation. The vaccine is less than 1% effective using the ARR. Now that's pretty daggone shocking. We went from being 95% effective to actually less than 1% effective. So which is it? Again, both of these are perfectly legitimate statistics. You can report either one of these and you're not lying. Now I'll leave it to you to wonder why Pfizer only reported the 95% efficacy. They did not report the ARR, but this is a perfectly legitimate statistic. Okay? It is telling you the absolute risk reduction. This is doing the same thing, but relative to where you started. So they're both perfectly legitimate. There's not really a strong argument from my perspective for one or the other. Now, some statisticians or epidemiologists might prefer one or the other, but they're both perfectly legitimate. The Kramer's V is legitimate. The odds ratio is legitimate. They're all perfectly legitimate stats, but they're telling you very different sorts of stories here. Okay, lastly, then we have the number needed to treat. And many clinicians find this fairly useful. Notice what I've done here is I've taken the reciprocal of the ARR, but I've turned it into a proportion. This is a percentage. To turn it into a proportion, I'll move that decimal 2 places to the left, so 0.0084, and then 1 divided by that, and I get 119.05. So just go ahead and round that, and the way you interpret this is I would have to inject 119 people to prevent 1 COVID illness. So now you want this to be a lot lower. Let's say we're 5. I'd have to inject only 5 people to prevent 1 COVID illness. That seems like a pretty good bargain, right? I inject 5 people and I prevent 1. Or think if it's like 2, if I inject 2 people and I prevent 1, that's really, really good. But here we're at 119, which is not very impressive at all. I've got to deliver or administer a lot of COVID injections. I'm sorry, mRNA injections. I've been misspeaking here. The Pfizer injection. I've got to administer a lot of Pfizer vaccines just to prevent 1 COVID illness. So this again makes it sound like the Pfizer vaccine is not very effective. But if I'm Pfizer, I'm looking at this, it's 95% effective. So we're in this kind of bizarre no man's land with all of these effect sizes. They're all perfectly legitimate, but they're telling you different stories. Now that's not always the case. It depends on the data. They may line up better for, other products, other medications or what have you. It may be that all of the effect sizes tell the same sort of story, that the medication's effective or maybe overall it's not effective. But oftentimes they don't add up real well. They don't match up real well. And for the Pfizer data, it's really quite dramatic, 95% to less than 1%, depending upon which statistic you use. So, quite fascinating stuff there. I suppose maybe we're back to the first day of class. There are lies, there are damn lies, and there are statistics. You can see here how folks could pick and choose the effect sizes that they like and report only those to sort of back up their particular claims for or against the Pfizer vaccine. But that's just the way the cookie crumbles. Is that the phrase? So that's just the way it is. So now you guys are better educated, more informed. And what we'll do is I'll post a video. I think I have another video, a YouTube video. We'll walk through another problem. We'll look at another problem, another medication or something on Tuesday. So we'll work through another one of these. We'll look at all these effect sizes. And I'll explain why that expected frequency formula works as well. And then that will prepare us. We'll hopefully have another quiz-am coming up here pretty soon on this chi-square test of association. All right, well, that wraps this up for the Zoom or online lecture that we're missing due to the, again, epic concert coming to Stillwater this week. All right, we'll see you all on Tuesday.